Okay, wonderful AP young people. Sorry it's taken me so long. It's been a busy evening so far. So here we go, partial pressures. Partial pressures are really simple. Dalton discovered this when he was talking about the atom and the fact that he was mixing gases together, and he said that the total pressure of the system must equal the sum of the partial pressures of each of the gases. So the total pressure has to equal gas A plus gas B plus gas C, and that has to be equal. So if I have three inert gases here, nitrogen, xenon, and helium, placed inside a container of a fixed volume, then I know that 3.44 atmospheres of N2, that's the pressure of N2. So I know the P of N2, I'm sorry, I'm making all kinds of noises and doing all kinds of things that I really don't want to be doing here. So I know that the P of the N2 is equal to 3.44 atmospheres, okay? An unknown amount of xenon, so I don't know the P of xenon is equal to X, okay? Let me see if I can erase that line because it's going to drive me a little nuts. Yeah, if I erase that line, then I get rid of the 4, okay, 4, okay. And then the P of helium is, again, my finger is not doing walking very well here today, guys, sorry. The P of helium is 678 torr. Okay, what is the partial pressure of xenon gas? Well, the first thing is I have to get the same pressures. Doesn't really matter what's happening here. I know that the total pressure in the container, P total, is equal to 6.10 ATM. Since I have ATM in two of them, I'm going to change torr to ATM by dividing by 760. When I divide by 760, I get that I have 0.892 atmospheres for that. So basically, the P of the N plus the P of the xenon plus the P of the helium has to equal P total. So I don't know xenon, so I know that P of the xenon is equal to P total minus P of the N2 minus P of the HE. So that's pretty simple, right? So I have 6.10 minus 3.44 minus 0.892. And what I get for an answer, I'm going to put that up here, what I get for an answer is 1.77 atmospheres for the xenon. It's pretty simple. All the pressures have to add up to the total of 6.10. So once you know two of the three, then you know the third one if you have the total. Pretty simple, right? Okay, so you can also use moles because moles and pressure are related to one another. So what we need to do is we need to find the individual pressures. You can use PV equals nRT to find each individual pressure, or you can find the total number of moles. So if you know the moles of X and the moles of Y and the moles of Z, you can add all those together and get the total pressure and then start working on partial pressures from there. So let's look at that. So if I know that I have 0.0812 moles of O2, so I know that, I've got that information right there, and I have 1.22 grams of carbon dioxide, well, the first thing that I want to do is I want to change 1.22 grams to moles. So I'm going to divide that by 44.01, that's the molar mass of CO2, over 1 mole of CO2, okay? And I'm going to end up getting that I have 0.0277 moles of CO2. So now what I can do is I can find the pressure of everything by taking nRT over V, but the N I'm going to use is the total N. This plus, sorry, my finger keeps doing the wrong walking here. Okay, let's try that again. Plus 0.0277 times 0.08206 times, let's see, 25, that's 298 Kelvin. Remember units, I'm not putting units in because my finger is not walking very well. And then the container is 0.265 liters. Remember the unit of this, I'm going to put it up here. Remember the unit is liters atmospheres over mole Kelvin, okay? So when I do that, I've got moles canceling out because that was moles. Liters are going out. Kelvin is going, ooh, back it up, back that train up. Kelvin is going out, and I'm left with atmospheres, so I'm going to get a total pressure. And I get a total pressure of 10.0 atmospheres. Okay? Pretty simple. I just have to find the number of moles. If I find the total number of moles, I can find the total pressure. Okay? So what if I wanted to know the pressure of each of those items? Well, I'm going to use something called mole fraction. Now, if I multiply by 100, become a percent. But remember, when we calculate, we use fractionals anyway. So we're talking about the number of moles of substance divided by the total number of moles. It's called mole fraction. It's not mole percent, it's mole fraction. So be really careful with that because that could be problematic. Okay, I'm taking my glasses off because there's glare and I forgot. All right, so why do we care about mole fraction? Well, then we can find the partial pressures of each thing. If we know the total pressure are the same ratios as the number of moles. So if we know the total number of moles, we know the total pressure, then we can find the mole fractions and find the partial pressures of each. So it's pretty cool. So we have three gases, A, B, and C. They're present in a flask container, pressure of 3.0. So we know the container has a P total of 3.00 liters, okay? So we know that it contains 4 moles of A, 3.23 moles of B, and this many moles of C. What is the partial pressure of B inside the container? Well, it's really simple. I need to add up all the moles to get the total number of moles. Okay, when I do that, I get a total number of moles of, let's see, 6.552. I only wanted to know the pressure of B, so what I'm going to do is I'm going to get the mole fraction of B. So 0.232 divided by 6.552, and that gives me a mole fraction of 0.354. So what I'm going to do now is I'm going to take 0.354 and multiply that by 3, which is the total pressure, okay? And then once I've done that, I get that the pressure of B in the container is going to be 1.06 atmospheres, okay? Pretty simple. If I know the mole fraction, I know the partial pressure. I could actually calculate the partial pressure of all 3 of those, but we just asked for B inside the container, okay? So, pretty simple so far, yes? It's going to get a little more complicated, but not too bad. So flasks, by thought processing, by opening a valve between 2 flasks, you're changing the final volume of the container. If you find the new pressure of each of the gas, volume and pressure using Boyle's law, then you will have the partial pressure of both gases. And then you can add those partial pressures up to get the combined pressure of the gases after the valve is opened, just by adding them together. So let's look at a problem. N2 is placed in the left flask, which has a volume of 265 milliliters and a pressure of 3.2 atmospheres. NO is placed in the right flask, which has a volume of 198 milliliters and pressure of 484 torr. The system is at 20 degrees Celsius. What is the total pressure inside the system after mixing? Temperature is constant here because both of them are at 20 degrees Celsius. So what we need to do, first of all, 265 milliliters plus 198 milliliters. Okay, that's going to give me 463 milliliters. That's the total volume of the two, not moles, sorry. Not moles, no moles. That's going to give me the total volume of those 2 containers, milliliters, okay? So now what I'm going to do is I'm going to use Boyle's law. Remember, P1V1 is equal to P2V2. I'm looking for P2, so P2 is always equal to P1V1 over V2. So I start plugging things in. The first one says that I have 1.32 atmospheres at 265 milliliters. And I'm now going to 463 milliliters. And what I end up getting is that the nitrogen, the P of the nitrogen, is going to equal 0.755 atmospheres. Okay, the second one is in torr. So the first thing I want to do is take 484 torr and divide it by 760, because that's going to give me atmospheres. And when I do that, I get 0.637 atmospheres. I plug that in over here, except this number is going to be different. So I'm going to put 0.637 atmospheres times 198 milliliters divided by 463 milliliters, and I'm going to get the pressure of the NO in the flask to be 0.272 atmospheres. Okay, I add those two together and I get the pressure total in the system is 1.03 atmospheres. Now, I did that just like that. You can also do it a different way. I also calculated the number of moles and then inserted that as a total and got the exact same answer of 0.103 atmospheres. So when you have two containers, you basically use Boyle's law to figure out the partial pressure of each of the gases once the container has gone to the bigger volume, and then you add those two pressures up to get the total pressure of the system after mixing. Okay, relatively simple. So when partial pressures are dealing with reactions, you need to find the moles of gas that are present from each part of the reaction. So you first have to look to see which one's excess and which one's limiting and figure out the moles. Once you find the total number of moles still around after the reaction, you can use PV equals nRT with the total number of moles. So it's not so hard, but there can be some slight complications. So let's look at a problem. This problem has a slight complication, so I want to show you. We have CO reacting with, and this is a gas, reacting with O2 gas to produce CO2 gas. All three of them are gases, okay? To balance it, let's see, 1, that's good, 3, okay, so that's not good. So let's double that. That's, okay, so there we go, balanced equation. So we know we have 1.32 grams of carbon monoxide, so let's go ahead and change that over right now into moles. 1.32 grams into moles, that's 28.01 grams of CO over 1 mole of CO. Okay, I know my finger is a little crazy, and we get 0.00471 moles of CO. That would mean that I would need half that much oxygen. So that means I would need a total of 0.00236 moles of O2. So how many moles of O2 do I have? Well, this becomes our problem. We have 112 milliliters of oxygen gas, but it's at 17 degrees Celsius. And we know that we have a certain volume. So what we need to do, we have this volume at this temperature, but what we really need to know is what volume it would be at STP, because that's the only way that we can convert to moles. So we're going to use Charles' law. Remember, Charles' law is V1 over T1 is equal to V2 over T2. We're looking for V2, so if we do that, we get the equation V1 times T2 over T1 is equal to V2. Okay, so we plug all of that information in. Basically, we plug in 110, 0.12, let's just put it that way because we're going to do that. T2 is 273 because that's the STP that we're looking for. This temperature is 290 at 70 degrees Celsius, and we get 0.105 liters. We can then change that to moles. Even though it's at a different temperature, it's going to be the exact same number of moles. I know that's a little strange, but remember, as temperature increases, the volume is going to increase. So even though the number of moles doesn't change, It does because of the temperature. And I know some of you are going to be like, what fresh heck did you get me into? So when we do that, we get 0.046, I'm sorry, 0.00. Let me add another 0 there, 0.469 moles. Clearly, we have excess amount of oxygen, okay? So that means this is limiting. So the partial pressure of the CO is 0, okay? Because there's none left. We're going to use all of that up, okay? So we don't have any of that. This is how much O we used. So what do we need to know? We need to subtract these two numbers so that we get the leftover. So if we subtract 0.00236, what we end up getting is 0.00233. That's the number of moles of O2 that are left. How many moles of CO2 are created? Well, if you look here, this is a 2 to 2. That means our 1 to 1. So if I have this many moles of CO that are used, that's the number of moles of CO2 that I'm going to create. So now what do I know? Now I know the total number of moles. So I have 0.00471 moles of CO2. So that means the total number of moles I have are 0.00704 moles. Since I want to know the total pressure inside the vessel after the reaction is complete, and I know that the pressure of the CO is nothing, these are the only two things that matter. So now I'm going to go in and I'm going to erase all of this stuff. I know you're like, oh my gosh, don't erase all of that. We got it, right? You've already written this down. Remember, you can stop it and go back and see that again. Okay? So almost finished here though. So I'm going to take that, and I know that P is equal to nRT over V. And so my N is going to be 0.00704 times 0.08206 times 290, okay, divided by, the vessel is 0.278 liters. Okay, and what we end up getting is that the pressure total is going to be 0.603 ATM. I tend to go to ATM. I feel like it's easier, it's kind of a regular number, and I understand it a little bit better. But this is partial pressures and how we can use them. So make sure you've taken these notes, because tomorrow we'll be applying them to some problems and doing a few things with that. All right, thank you.